This example is referring to the connected trees. So we do have some random points on the surface. Suppose here we have 10 points, and what we want to do is try to find out the graph, which is a tree without any loop, which is a connected one. Okay, so we want to find a connected graph which has no loop inside it. Okay, so in order to solve this problem, we need to find out a way that first of all we need to find a connected graph and then try to avoid having any kind of loop. Okay, so in order to do so, we need to think about how we should do that. First of all, in order to make the graph connected, first of all I put some demand on each point, a virtual demand, so it doesn't exist in reality, but we want to find out a way that how can we supply all of these demands. So in order to do so, I assume that I have a generating unit at one of the points, just one of the points. Let's say point number 1. You can put it everywhere else, and then try to find a way that connect these production point or generation point to the rest of the points. Okay, and if you can formulate that, then it will be solved. Okay, so let's think about what kind of variables do we need in this formulation. Okay, this example is referring to the problem of connected trees. Let me describe the problem for you. First of all, we do have a number of points scattered on a surface. Suppose we do have just 10 points in this example, and in order to solve the problem, we need to think about two different constraints. First of all, the graph should be connected and it is a tree. The definition of the tree is that it's a connected graph without any loop. Okay, so how can we solve that problem? Okay, in order to solve that, I assume that at every node there is a virtual demand that should be supplied. So every node has a demand, no matter what the amount is, but we know that this demand should be supplied. And in just one of those nodes, I put a production plant, and that production plant should be able to supply every demand in the system. So this will give us the condition of connectivity. In order to do so, let me think about what kind of variables do I need. First of all, which node should be connected to each other? So then definitely it will be a binary variable. Let's name it uij, and dij is the distance between node I and j. Okay, and for every node I have to write down the balance of supply and demand. So at every node, gi minus li is equal to the outgoing flows. But keep in mind that only one of the nodes has gi, or generation or production. Okay, just node number 1 or any other nodes that you want. For simplicity, I chose node number 1. And also there's another condition. The flow only can exist on the lines that are connected to each other. For example, let me give you an example. For example, if 1 is connected to 4, then uij is 1. Then flow can get a non-zero value. So the flows are assumed to be positive as well. Okay, so if I solve that, then the connected tree can be found. So let me show you the Python code. So beginning, first of all, as usual, we have to import the required packages like Pyomo, Matplotlib, NumPy, and also the random. And then I create a model, an abstract model. Model n is the number of nodes. For default value, I put 8. But you can change it. I made it mutable. It means that you can update it. Model I is the set representing all the nodes from 1 to n, and also j is the alias of I. Model u is the variable, is a binary one, indicating I is connected to j, I to j. Flow, that's the same, and I define it as a non-negative real. G is the variable representing how much you are producing. I defined as just one variable. It's not needed to be defined over a set because only one of the nodes has production or generation, and the objective function at the end. And so maybe we need to initialize some variables like x location and y location. These are not variables, these are parameters, because we already know where these points are allocated. In order to initialize the parameter d, which is the distance between each pair of nodes, we have to define it as a parameter here. You can see it's over model I and j. It takes non-negative real numbers, and I initialize it using this rule. This rule is the famous rule, sqrt of x location I minus x location j square plus model y location I minus model y location j square, and this will give the distance between each pair of nodes. It's a parameter as well. And the balance equation, which is written on every I, is defined using this rule. So for the first I, we want to put g only on the first I, and for the rest of them there is no g here. Okay, and here this quantity is the virtual demand at each point, so I just defined it as the I divided by model n. So and that's it. What else is remaining? Rule number C2 is the fact that if u is non-zero, then flow can get a quantity, and also the objective function is multiplication of urc multiplied by drc for every r in I and c in j. Okay, and also what else is remaining? The objective function is model.of, the sense is minimization, solver is glpk, and model n, let's assume there are 10 points. I initialize the instance, solve the instance, and print the objective function. And also, first of all, I draw the points, random points, generated points, and also show the solved results. I rerun the program. This one, since the points are randomly generated, each time you plot the graph you might get a new one, but that should be fine. And the program is running. So you can see here that generation is on point 1 and it is trying to supply every node. So the nodes are like this, but when you solve the problem, the connected tree is here. So why is it always tree? Because if you add any additional line, then an extra cost will be added to the objective function. So the program naturally will avoid that. It is not only connected, but it avoids any loop. Thank you very much.